Good afternoon, everyone. Hope you enjoyed the conference so far. I'm looking forward to the dinner after. I know I'm looking forward to drink reception, to be honest. I'm here today. My name's Fergus. I'm from the University of Manchester. The title of my doctoral studies is Particle Transport and Loss when Sampling Aircraft Combustion Emissions. It's a little bit of a mouthful, but yeah. So as I said, I'm at the University of Manchester, studying under Paul Williams, and I'm sponsored by Rolls-Royce. So today I'm going to talk about one of my most recent studies, which is charged aerosol particle loss through aviation NVPM sampling systems. So let's start with a brief overview of what I'm going to present. So I'm going to give a quick introduction to aircraft gas turbines for those of you who don't really know what they are. Then talk about the emissions that are associated with these. Then talk about the standards and regulations around sampling these emissions. Then go on to the aerosol loss processes associated with sampling these emissions, talk about the experimental design, talk about the effects of charged aerosol particle loss on carbon-loaded PTFE sampling tubes, then talk about the effect of changing the tube length. So this is a basic schematic of an aircraft gas turbine. There's four main sections to this. There's the compressor. This compresses air. This compressed air then enters the combustion chamber, where it is mixed with fuel and ignited. This ignited air-fuel mixture is then allowed to expand through turbine blades, and then it exits the engine at the exhaust. This fuel-air mixture is what we call emissions. These emissions comprise of a complex mix of gases, volatiles, semi-volatiles, and non-volatile particulate matter, or NVPM. I'm particularly interested in NVPM. NVPM is a solid carbonaceous aggregate change at usually below 100 nanometers in diameter. So why do we care about sampling NVPM? Well, aviation NVPM accounts for around is estimated to account for around 16,000 premature deaths annually. Also, aviation NVPM is the main anthropogenic particulate matter in the upper atmosphere, serving as cloud condensing nuclei, scattering and absorbing incoming radiation. Due to this, the International Civil Aviation Organization have introduced a new global NVPM reporting standard. Further to this, Rolls-Royce are particularly interested in characterizing and developing improvements to reduce their emissions and improve their combustion process. But this has to be done on test rigs. To do this, the true engine exit NVPM concentrations are required. However, at the engine exit, harsh conditions are witnessed, such as 700-degree temperature. Due to this, long sampling lines are required to take the hot sample, cool it, and transport it to the measurement instruments. However, on long sampling lines, large NVPM concentration losses are witnessed. To account for these NVPM concentration losses, models have been developed. These include corrections. One such model is United Technology Research Center model, published in Aerospace Information Report 6504. So there are 5 main aerosol loss mechanisms associated with sampling NVPM: thermophoretic loss, diffusional loss, electrostatic loss, bend loss, and inertial loss. In this study, I mainly focused on electrostatic loss. The electrostatic loss is the motion of charged particles in an electric field. This can be external to the sampling system, on the sampling system walls, or on the particles themselves. The electrostatic loss has 3 main aerosol loss mechanisms. Image force on tube walls. This is when charged particles deposit on tube walls, setting up electric field. This then creates more particles, so this then creates a charge which attracts more particles that deposit on the tube walls. Coulomb force of charged particles in an external electric field. This is when an external electric field forces the particles to deposit on the tube wall. And the electrostatic dispersion effect of particles of the same polarity. This is when a large number of the same polarity particles repel each other and force the outermost particles to deposit on the tube wall. In most sampling systems, the top 2 loss mechanisms can be mitigated by using conductive tubing. So in most models, the bottom mechanism is the only one considered. Looking at the figure, we can see a breakdown of the 5 different loss mechanisms for a typical NVPM sampling system. As indicated by the red circle, we see that the electrostatic loss accounts for about 1 to 5% of the total losses. This is usually due to a couple of assumptions. One of the assumptions is that all the particles coming out of all the MVPM particles coming out of the combustion engine are singularly charged. This is still yet to be quantified. Also, that the tubing and the whole sampling rig is completely conductive. The figure here shows a schematic of the sampling system that I've developed earlier in my PhD. The key thing to note here is a dual SMPS CPC system, which conducts a differential measurement over a test section. The test section used in this study is carbon-loaded PTFE of 6 mm in diameter. More tube materials have been used with different diameters. However, this will not be presented in this presentation. For this presentation, a varying tube length, applied aerosol charge, and flow rate have also been studied. For this presentation, the aerosol materials used are silver diluted by nitrogen, silver diluted by air, and salt to cover a range of particle sizes. So let's go on to some results. So looking at the effects of charged aerosol particle loss on carbon-loaded PTFE sampling tubes. Let's start by looking at, what we've done there. Is this what it is? So let's start by looking at this top uncharged line. This is the purely diffusional line, and comparing it to these two bottom lines, which are the highly charged particle lines, positive and negative. We can see that there is a large increase in particle loss due to the electrostatic effect. We're around 50% at the smaller size ranges. Now comparing these two lighter colored lines, which are the low charge lines, and comparing them to the highly charged lines, we see that as the charge increases, more particle loss is witnessed. Now comparing the dark green line and the dark blue line, which represent positive and negative charge, we see that there is minimal impact on the polarity of the charge on particle loss. In this plot, I've included two models. The dotted black line at the top is a purely diffusional model, and the dotted red line beneath it is a combined diffusion and electrostatic dispersion model. Comparing the bottom line against the two highly charged lines, we see that the model significantly underpredicts the losses. Also note this characteristic trough between 7.5 nanometers and 17.5 nanometers. This is still under investigation. Taking that highly charged line and investigating a little bit further by changing the flow rates going through this to account for 4 flow regimes. So first let's look at the blue line, which is transition flow, the green line, which is turbulent flow, and a purple line, which is a highly turbulent flow. We see minimal impacts on flow rate here with charged particle aerosol loss. Now comparing this to the pink line, which is laminar flow, we see that there is the laminar flow has slightly less losses than the other two. This is probably just due to diffusional losses being less for laminar flow. Now looking at the effects of charged aerosol particle loss on sampling tubes of different lengths for 12.5 nanometer salt particles. First, let's compare the uncharged line, which is this orange line at the top, against this highly charged line, which is blue line. We see that as the tube length increases, the particle loss increases for the electrostatic loss effect. This suggests that electrostatic loss is tube length dependent. Further to this, we see that the majority of losses occur between 1 and 2 meters. Now comparing the two models from the previous slides in this slide, we see that, again, the model is significantly under predicting the particle losses. Now looking at the effects of charged aerosol particle loss whilst changing the tube length for 30 nanometer salt particles. Again, comparing this orange uncharged line against this blue highly charged line, we see a similar effect, mainly that the tube length is dependent, that the aerosol loss is tube length dependent. And the same effect in terms of when comparing the model lines against that highly charged line. However, electrostatic losses are seen to be a little bit less than for 12.5 nanometers. So just to summarize, to mitigate growing concerns on public health and the environment, MVPM regulations have been put in place. Models are used to correct for MVPM concentration loss when sampling along sampling tubes. One such mechanism that is included in these models is charged particle loss. Current models underpredict charged particle aerosol loss through carbon-loaded PTFE sampling tubes by up to 50% at the smaller size ranges. From the last two slides, charged particle loss is tube length dependent, with the majority of losses occurring over the initial 1 to 2 meters. So some further work for this study would be to compare other sampling tubes such as stainless steel and carbon-loaded silicon, measure and confirm that aircraft gas turbine combustion MVPM is highly charged, and investigate applying the other two charged aerosol particle loss mechanisms in a model. Thank you very much for listening.